So let's continue to talk about OpenMP. Specifically, we're going to talk about work sharing. So a work sharing construct divides the execution of the enclosed code region among members of the team that encountered it. So there's different models. So I can have a for loop where I want to share the iterations of the for loop across the different threads. I might want to separate it so then each section is executed by a separate thread. So that is the example I gave you in the previous video where the master thread only executed a specific portion and the other threads executed some other portion of it. And then we can also have it so then we can serialize the execution of a thread. So this is where we might have a critical section for some important part, though we might have some other general parts that we want it so then all threads can execute with. So here's another useful item in your tool belt for OMP. This is the Pragma OMP for directive. So this will automatically split up a for loop for you, which is very handy. So if you put it within a Pragma OMP parallel block like this, all you have to do is say Pragma OMP for. This is the only directive in the parallel section that is allowed. You can actually shorten this though and put it directly over the for loop. So you don't actually have to have the Pragma OMP parallel block. You can just directly put this Pragma OMP parallel for on a for loop and it will automatically figure out, okay, I have a for loop here, so that is the parallel section that I want to do. It will automatically manage this for loop for you and split it up into the ways that are needed. So in general, how does OMP actually work with a for loop? So it breaks this loop into chunks and allocates each chunk to a separate thread. For example, if I set max to 100 and I had two threads, I would assign the first thread to 0 to 49, and then the second thread would be 50 through 99. This is automatically done for you by OMP, which is very nice. Though the thing is OMP is kind of dumb in the sense that it requires a very simple shape for the OpenMP aware compiler to be able to parallelize it. So it is necessary for the runtime systems to be able to determine how many iterations of the loop will be assigned to each thread, because if it doesn't know the number of iterations, how does it know how to split it up? The other thing is there cannot be any premature exits from the loop, so that means you cannot break, return, exit, or do goto statements. Those are all restricted. Another shape restriction is the for loop cannot be a do-while loop, or a loop without loop control. Also, the loop iteration variable must be an integer, and the loop control parameters must be the same for all threads. So those are some of the limitations you have. And one thing in general is you should never jump outside of a Pragma block because that's just bad practice, mainly because you have multiple threads and you have no guarantees of what's going to happen next with those threads. So here is a little bit more information about the Pragma OMP parallel for directive. So a master thread will create additional threads, each with separate execution contexts. All variables declared outside of the for loop are shared by default, except for the for loop index variable, which is private per thread. You might be wondering why. Well, after all, I want it so then each thread might be executing something based off of a specific thread ID. For example, maybe I want thread 0 to be writing to the 0th item of my array. If I have it so then that index variable is shared, I might have thread 1 execute and then thread 2 execute, so it might change the index variable, so then I might be using the incorrect variable essentially, or the incorrect number for that loop index, or for that loop iteration for one of the threads because of this shared variable. So that's why they're all private. The other thing is we divide the regions sequentially per thread. So this means thread 0 will get the first portion of the items, thread 1 will get the second portion, and I have some equations for how you would do it with n threads. For example, if I had two threads and I had 100 items in my array, I'd have the first thread do 0 through 49, and then the second thread do 50 through 99. You might be wondering, why do we do it like this instead of like, say I had two threads, I want the first thread, which is thread 0, to execute the even ones, and thread 1 to execute the odd elements in my array. Maybe I want to just set everything to 0. Why might that be a bad idea? Well, the reason why this is bad is because of what you might have learned already with caching. So each thread might be running on separate cores, which means they might have separate caches. So what the issue is say I have it so then thread 0 executes and it does a write operation. What this means is it's going to invalidate the other caches lines that might have that array in them, which means that when thread 1 executes and it might write to the next item, it's going to have to invalidate essentially the other thread's cache, and then it's going to have to do the write. But then maybe thread 0 executes again. So thread 0 is going to see, oh, my cache line is invalid, so I need to now pull in that data. So it's going to have to fetch it from wherever thread 1's cache is, and then it's going to have to write to there. But once again, this is going to invalidate thread 1's cache. So this idea is called false sharing, where essentially the threads are sharing something but it's not really sharing it in an efficient manner because they're not actually modifying the same value. There is this thing called true sharing as well, where I'm actually modifying the same value from different threads and it's causing invalidations. So that's what true sharing is. False sharing is when I'm not writing to the same location in memory, but causing other caches to get invalidated when they needed to write to different locations in memory. Also, another thing is there is an implicit synchronization at the end of the loop. So once the loop completes, all the threads will join back up, so then we can run our sequential master thread once again. Also, we also implement cache blocking as it allows us to have much better AMAT.